let's continue our discussion on cascode structures. As I said, the feature of a cascoding structure is that the gain is being boosted mostly because, if you think about it, if you use transconductance model, it's basically transconductance of a single transistor and being times its output resistance. Therefore, if you think about a cascode amplifier, let's look at some variation. Our previous discussion, we're using a load. Use an ideal current source. That's the maximum gain you can get. So whatever we discuss is the most ideal case. But in real case, we don't have an ideal current source. What we have is just a real whatever current source you can make. So if you think about it, if I give you this example, or I'm just using a resistive load, what do you expect the gain will be? So this is VB again. And we can do both of them. So we know that the output resistance at this particular point is the resistance looking down and RC. If you're using an ideal current source, then the resistance looking down will then dominate because it's infinity otherwise. But in this case, if I'm using a relatively small resistance, just typical resistance is not that large. So this is the input-output. Once again, cascode amplifier input-output. For the circuit on the left, it will simply be, for the BJT version, you will then have a voltage gain. I'm just going to write voltage gain. It's minus GM1 R out in parallel RC. We know that R out in this case is beta RO. So it's definitely much, much larger than RC. So you would then get minus GM1 RC. So there's no gain in your ultimate voltage gain because it's the same as when you remove Q2. You didn't get too much because it's limited by your output resistance. It's the same for MOSFET. Your voltage gain will be minus GM1 times R out going down and in parallel with RD. Right? So we know that this is GMRO squared, which is much, much larger than RD. Therefore, you still get minus GM1 RD. So basically, there's no overall gain. It's the same as you remove M2. Right? So in order to maintain this high gain, this is the same as an analogy as if you compare to our quarantine process. If you're not quarantined high enough from the above, so if you're only quarantining like people coming from outside and no quarantine from people within, then you actually get this leak, this low resistance path. Therefore, the low resistance path will then dominate. Then you won't see the blockage effect of this high resistive because this is in parallel. So low resistance will dominate. So whatever you build up as your high output resistance will not maintain, right? So how does one? So one of the key important thing is to, if you want to maintain the high ideal gain, actually it's a high ideal voltage gain of a cascode amplifier, is to build, you need to have a good, I should say more ideal current source load. That's one of the key things. As it's the same as another analogy is that if you do an insulation of the house, if I'm only isolate the left and does not isolate the right, then the heat or the heat generated will leak out through the weaker spot. It's the same as a resistance. So you need to protect yourself with the high impedance node with both sides cascode. So to actually do that, you need to have, so how does one maintain this high output resistance? So the key is to make sure that your output resistance does not degrade drastically. I lost my color. Okay. So to do this is to use cascode current source as load for cascode amplifier. OK， 这就像我们讲清零，你要清零，你就是上下都要做，你不能只做一半，你做一半你就漏。So it's the same. You have to make sure that you want to isolate make sure that there's no leakage path. If you have any leakage path, then it will just break in. Okay, so it's the same thing. That's actually the same difficulty. If you think about it, is that you need to isolate the node very well in order to provide the gain. So it's a painstaking process if you're doing this type of structure. So you need to make sure that the nodes are very well taken care of, and there's no leakage path from this output terminal. So let's look at an example. So as I said, I'm using a bipolar example. Q1, Q2, input, output. So this is the basic of my cascode amplifier. So underneath, this is the cascode amp. And then we need to stack it with a cascode CS, current source. So the cascode current source will be something like this. Because it's the sourcing current source, we need to use PNP. So this will be VB1, VB2. I need 3 bias voltages, and then this will be my VCC. So you basically have to stack up the top and the bottom to isolate this particular point. The key is to show that R out is RON in parallel ROP. So RON is looking down using MPN. ROP is looking up for PNP. So you need to make sure that both of them does not leak. There is a very, very low leakage, high impedance. So high impedance node is a high maintenance node. You need to make sure that every pathway is being blocked. Okay? Q3, Q4. So you need 2 PNP. So 2 PNP for cascode current source. You need 2 MPN to construct the cascode amplifier. Okay? Good? So how does one maintain? The gain will still be the same. We know that the voltage gain will be minus GM1 because this is the key modulation factor, even though all of them should be the same. There might be difference between MPN and PNP. But basically, it's GM1 times R out. So what is R out? Will be RON in parallel ROP. So RON will be beta NPN, RO in parallel. I should just be precise. Beta PNP times ROP. even though both transistors may have the same Wiley voltage, but we know that in most cases, beta PNP is much, much smaller than beta NPN. Right? It's at least maybe 4 times the ratio. Remember, what's the ratio between the two? If we're making the transistor size identical, doping identical, what is the ratio? The ratio is determined by if the size and doping are the same. Doping level is the same. So let's say if you have a mobility ratio of maybe 3, that will be a 9-fold difference, right? Because its beta is much, much lower. The main reason is because its base current is electron current, Hole current is, for PNP, Hole current is the collector current. Right? So review this a little bit. Just get a sense as to the ratio between the two. It's more than 5 in most cases. Okay? So that will then give us, this will be the more leaky component from the top, because this will typically be the dominant component. Okay? Good? So let's look at an example. So we're going to finish up this discussion of a cascode stage with a complete example of a cascode amplifier with cascode current source load. And we're going to talk about the trade-off and how does one analyze its key operation, the 3 key parameters, and also what is the target? So the target is to find your Rin, voltage gain, RL. And then the second thing is to find VO minimum. We call the output, this is called the output swing. What is the maneuver room of this amplifier, allowing the output voltage to change? So I'm going to use an example. A real operational MOS cascode amplifier will look something more like this. Remember, you have 2 at the bottom end channel for amplification. Let me ask you one question. Why don't I want to flip it? Why don't I want to use this as the amplifier, this as the current source? Why? Why does we typically use N channel or NPN as an amplifier, P as the load? Does anyone know why? Okay, you can think about it, but it's actually more prominent in MOSFET, BDD. So I have 2 PMOS as the current, it's the same. This is the, this part. Okay, let me write it down first. So I have 3 biases. I'm just going to give you the voltages, okay? So this is my V in. This is my V out. So I have 4. So for example, you would then be faced with this type of question, for example, in the final exam. I will give you something like, for example, this is an example circuit. And I will ask you, what is M1? What does M1 serve? You should know that M1 will serve as a common source stage. This will be a common base stage. And 3 and 4 will be the cascode current source. You should be able to identify what are each of the transistors, their role in a circuit. Okay? What are the roles they're playing? So as I said, this will be, if I'm highlighting, M1 is common source, M2 is a common gate, and 3 and 4 will then construct a cascode current source. So the first thing is that you need to identify what each of the transistors are playing their role in this particular circuit. Okay? So let's give parameters. So let's assuming that we design so that the drain current of all transistors, all 4 transistors are the same, because we only have single branches. Therefore, there's no beta effect. There's only one branch of current, which is 100 microamp through this particular branch. And then, of course, we have transistor parameters. That's 100 microamp rho square. And then because if I'm having the same Cox, because the mobility is 2 to 3 times lower, so this is 50 micro. And then I have threshold voltage VTN equals to VTHP equals to 0.5. For CMOS technology, you basically want to have more symmetric behavior of both. So even though mobility, there's nothing we can do about it, but for threshold voltage, you want to make it as symmetrical as possible. There's ways to manipulate so that it will be mostly identical. And the channel length modulation are also the same. We're assuming that they are the same. Okay? So I'm making two transistors. One is defining W over L. 1 equals to W over L2 equals to 8. And then I'm assuming W over L 3. So 2 PMOS are the same, 2 NMOS are the same. So this will be slightly smaller. Just want to make sure I'm using the right number. So what we need to do is that you're supposed to determine, so the questions are, you need to answer these and output swing. But before we do that, you need to answer, of course, to find VB1. And then the second part is to find its voltage gain. And lastly is the output swing. Output swing. So how does one approach these questions? So you need to determine these 3 biasings so that your IDQ is 100 quiescent current. Okay? We should also be able to identify what is the DC bias Vin. So this is the DC level of input voltage, of input, DC level of input. Okay? So let's see how one approached this question. First of all, we need to find out what is the overdrive of the circuit, each of the transistors, so that it will sustain a current of, so ID equals to 1/2 mu n Cx W over L1 VOV1 squared. Okay? So through this, we should be able to get our overdrive for each of the bias. So this will be, you just simply insert the number, and or VOV1 will be the 2IDQ divided by mu1 Cx W over L1 square root. Right? So the same equation, because I know the current, I know all the device parameters, so I should be able to divide what is the overdrive at the bottom. So we know that the overdrive is equals to 0.5 volt. You can do the same thing for, this is the same for VO because it's the same current. So the overdrive for transistor 2 is the same as transistor 1. You can also do the same for 3 and 4. So this will be the same IDQ. The only difference is that instead of mu n, it's mu p Cx W over L2. Okay? So you can get that the overdrive is actually 1 volt. So once we know the overdrive, we know that this will then tell me that VGS1 equals to VGS2 equals to equals to overdrive plus a threshold, so which would then give me 1 volt. That's for NMOS. So VSG, so this would then give me VSG3 equals to VSG4 equals to VOV plus a threshold as well. And this will be 1.5 volt. So once we know this, we can then determine our biasing condition. Okay? So this will tell me, let's say, I'm going to give a high voltage, otherwise there's no room for operation. So let's say VDD is 5 volt. Then this will be a 1.5 volt drop, VSG4. So this will be 3.5 volt. Okay, this is already known. And we know that V in should be VGS1. So it's 1 volt. Right? So V in DC level. This is already, we know this is 1 volt, this is 3.5 volt. So how does one determine VB2? It will be determined when you determine this point. Because this point is undetermined. So what we typically do is that we want to make sure that this is the highest level, meaning that this is 1 overdrive. So this, we want to set this to VDD minus VOV4, which is 1 volt. You want to set it to this point. So remember, there's a voltage drop of 1.5. Therefore, we want to set it, this is VD, so this is 3 point, did I get it right? VOV is, overdrive is 1 volt, right? 1 volt. So this is 4 volt. You want to set it to 4 volt, therefore, this will be 2 point. Okay? So from the bottom, this is the same because this is 1 volt. You want to set this to VOV1, which is, let me be precise. You want to set this node to VOV1, which is 1 overdrive, which is 0.5 volt. So you stack it with this voltage. It's a different color. We stack it with VGS of 1 volt. This will make this 1 point. volt. Okay? So this is 0.5. The difference between the two is 1 volt. Therefore, this is 1.5. So we get all the points. BB2 is 2.5. This is 1.5. So we get all the bias. As I said, this is not necessarily the only answer. You can actually set this to higher than you can set it to higher than 0.5. This device will still operate in saturation. You can set it to 1 volt, but then it will then limit your room. So this is the maximum you can get. You want to set it as low as possible. So I'm setting to at the boundary, but you can set it to 1 volt, but just gonna eat up your margin. So this 2, I should say, this 2 is the exact number. The number should be finite, but this 2 can be adjustable. It can be lower than this or higher than this. So this is not an absolute number. 这个是绝对的答案，这个不一定，你可以设，但是我们这边是为了要把它设到最低，so lowest level, so this lowest allowable, so to maximize your output swing. This is not necessarily the answer. You can set it a different way, but it will eat up your margin. Okay, so we're going to go and then check on. So we get all this part. So let's look at its voltage gain. So to get voltage gain, the first thing you do is to find transconductance. So transconductance, we need GM1 equals to GM2. We know that they're identical transistors. Therefore, there's various ways of doing this. You can do it with mu and Cox W over L1 times ID. And this will give me 0.4 milliamp per volt. Okay? And then for GM3 and 4, it's the same. We're going to use the same equation, which is the only changes in device size as well as the current's the same. Okay? The only difference is that a different device size at mu p. And because both of them are twice smaller, therefore your overall transconductance is, I set it up so that we get a clean answer. Okay? So once we get this, to get our final results, we also need the output resistance. We know that RO1 till 4 is the same because it's the same branch of current, the same lambda, equals to RO, which is lambda IDQ. Because lambda n equals to lambda p, then this will give me 100 k ohm. All of them are the same current, the same lambda, that will give you the same output resistance. So to find output Rn, there's no discussion. So let me just write it down. So once we have all this prepared, Rn is infinite because we're looking in from the gate. Voltage gain is, remember, is GM1 RO, I should say R out. Let me write R out first. So your output resistance is, if I writing down it more precisely, is the M2 amplify the bottom, so it's M2 RO2 amplify RO1 in parallel M3 RO3 amplify RO4. Okay? So this is just go back and look at cascode structure is the stage in the middle, the intrinsic gain of the stage in the middle times whatever you look at the source terminal of that intermediate point. So I'm just going to insert all the numbers. It would simply give you 1.3 mega ohms. So it's being boosted by a voltage gain. Even though it's in parallel, so that's your overall output resistance. And my voltage gain is minus GM1 R out. So that it will be minus 0.4 milliamp per volt times 1.3 . So the overall gain will be about 500. Okay? That's pretty high for a single stage. Typically, for a MOSFET single stage amplifier, typically deliver gain under 100 or maybe 50, around 50. So this is about doubling the gain of a single stage amplifier. Okay? So once we build this Cascode amplifier, the last part is to determine its output swing. So I'm simply just going to use this. So what is your VO minimum? VO minimum is limited by M2. So this is the same as our analysis on current source. VO minimum is limited by VB1 minus a threshold. Okay, so VB1 we already know is 1.5, so the lowest voltage it can go is 1 volt. And VO maximum is limited by M3, so it's VB2 plus a threshold because it's a PMOS. So that will give us 3 volts. So overall, what happened is that your margin, even though I have 5 volts, it will take away 40%. You only have 2 volts to move. So I have this large stage. I only have 40% where I can move. The lowest. So your margin between the two, this is 1 volt, this is 3 volts. So you start with rail to rail. Remember what rail to rail means. Rail to rail meaning the whole stage is 0 to 5. I have 5 volts, but I only have 2 volts margin to move. So only 40%. So that's the main challenge of Cascode structures, especially in advanced technology node, because when VDD scale, for example, if I give you 5 volts, there's still room to move. If I have VDD, you can do some exercise. So it has high. So the feature of this circuit is that it has high gain and high RL. But then it will have very low, poor output swing. The margin from top and bottom would then eat away your margin. So how does one improve your output swing? If you think about it, your VO max is limited by VDD minus 1 overdrive, 2 overdrive. So it's VO1, VOV4, VOV3. Your VO minimum is limited by VOV1 plus VOV2. So essentially, if you want to increase your margin, so how does one, if you ask you how to improve output swing? So if I want to make sure that my moving margin, the space that I can move, extend further down, what can be done? So this can be done by reduce overdrive. So think about it. How does one reduce overdrive? So your overdrive will then be determined by this. So as a designer, what you can do is to first look at this. You can reduce IDQ. Second, you can increase W/L. But then both of them will lead to a problem which we will not discuss yet, but we're going to discuss that in chapter 11. Both of them will lead to IDQ will then make your current smaller, meaning that your charging speed will then slow. And W/L will make capacitance higher. So this will then, the reason why speed decreases, your current decreases, and capacitance increases. W/L meaning that you have larger transistors. Remember, transistors are parallel plate capacitance. So the larger it is, it has higher capacitance. We're going to talk about that later, but just to give you a sense as to anything you do, a design problem is always a trade-off. There's always boundaries as to what is the secondary impact on your movement, or when you improve one parameters, what are the other things that you need to consider, or subsequent effect on your overall circuits, okay? So any questions? I still have one page to go, so we should be able to start a little bit on the introduction of a current mirror. Still have 10 minutes to go. One page, okay? So let me try to limit myself to one page. Okay, speed of the circuit is, if you think about it, 如果你想象一个电路的速度，很简单的想象一个电路速度。电路速度就是，你有一个电容，然后呢，你要让它，譬如我希望这个节点动，对不对？所以它节点动的时候呢，一定是你对它充电嘛。所以充电就是电流，所以你的水桶是不是能够很快的跟上？这就是速度。所以呢，如果你的电流越大，表示你水开的比较大，是不是跑得比较快？水桶比较容易满。还有另外就是水桶的大小，水桶越大，你就是动得比较慢嘛。所以你可以想象它那个冲水的速度，就算一样的水量，冲水的速度就会比较慢。所以速度基本上就是跟电流跟电容有关。那我们刚刚讲 IDQ 降低，基本上就是你的充电电流，你 overall 的电流会比较小。那第二个呢，就是电容，就这两件事情同时会让你的速度，这个会让你的水量比较小，这个会让你的筒子比较大。好 ，WL 因为什么是 WL 呢？就是W 跟 L 的 size 变大的话，基本上你就会有寄生电容。你可以想象，因为我们的 MOS 它实际上就是一个平行板电容器，它 essentially 就是一个平行板电容器，所以它的结构越大的话，它的电容就会越大。你需要充的电容就越大。所以通常大部分，如果你看数位电路的话，它的电容就是正比于 W 乘以 L 这样。那当然类比不一定啦，所以类比有其他的 issue 这样子。那我们到后面，但是这个 trend 本身是还是 follow 的。OK, good. Any questions? Should I skip current mirror? Would that be too much? 还是我下次再开始？我让大家问问题好了，我说再讲一个新的，怕大家等一下消化不了，会消化不了。Okay. So let me give an overview on Cascode structure. So one of the key challenge 有问题吗 Any questions? So you can think about it. Let me just talk about Cascode structure a little bit more. The reason why you don't actually see too much Cascode structure, especially in advanced technology node, is one of the things you need to understand is that something called for integrated or CMOS technology. I didn't actually spend too much time, so let me just say something. One of the key, I should say, highlight or catchphrase is called the technology node. Conventionally, so for example, the ones that we commonly see as we call the more legacy process, 经典制程。经典制程就是现在什么很缺的什么车用 IC 那种，那它就是 它的 technology node 呢，通常是 refer to 传统啦，当然现在有一点点。我讲一些题外话。minimum feature size， 什么叫 minimum feature size 呢？就是你在刻这个 IC 的时候，我们是有点像，我不晓得大家知道不 IC process， 它有点像刻印这样子。所以呢，你可以做最细的线呢，我们叫做 minimum feature size， or minimum minimum line width， 另外一个名词是 minimum line width。所以 if I'm saying that the technology node is 0.18 micron， 就是它最小的 minimum feature size 就是 0.18， 你最小可以画的线宽，好，就是这么细。那通常呢，因为你最重要做的事情就是要把 technology 的 transistor 特性做得最好，所以 transistor 特性里面呢，跟它最有关的，通常就是最小的，我们都来用什么去 define 呢？就是所谓的 length， 就是 gate length。也就是说，我可以做到最小。那什么结构我希望做到最小呢？就是它的 gate length， 就是 transistor 的这个。如果大家记得，就是 transistor 长这样嘛 ，top view， 这个是它的 gate。那它的 gate 的这个宽度呢，就是 gate 的长度啦，这个是 W 嘛。所以通常最小的这个技术呢，就是拿来画这个最细的线，就是 gate length。那当这个东西缩小的时候呢，通常就是 technology scale 的时候呢，当你的譬如说 L 往下缩的时候，通常的状况就是你的 VDD 就是 supply。那主要的原因是因为我希望我的电场，譬如说我的水平电场是基本上就是这个嘛，主要是这个。我希望我的 transistor 就算去往下缩，它的电场都不变，这个叫做 constant。我有点讲到外面去了，就是 constant field scaling。所以意思是什么呢？意思是说，如果我用比较宽的，比如说我们用比较0.25的 technology， 那它的 VDD 就是我画一个表，正常大家比较常见的这个所谓的 legacy process 呢，你的 VDD 跟你的 gate length 的关系大概是这样。我们大家比较常见就是0.18 micron， 这都是 micron， 0.25或是0.35。那它的 VDD 呢，就是 1.8 伏、2.5伏、3.3，这是标准。就是它为什么要这样做？就是我刚刚讲，它为了要让它的电场，transistor看到的电场是差不多的。那这样的话呢，就是你越小的技术，越 advanced 技术呢，就是你的 supply voltage 就会越低。那这会遇到一个问题，就是你可能3.3伏的制程。或者是5伏啦，假设大家更做比较大一点的元件，可以到5伏，5伏就是 0.5。我这边呢，如果给5伏，就表示我是用 0.5 的技术。那所以呢，我用 0.5 的技术，如果我今天想要用0.35做这件事情，我会遇到一个问题，就是我被压缩的很小，我的空间很小，所以我没有办法做 cascode。我一做 cascode 我就没办法动。所以这个是 technology scaling 会导致 cascode structure 呢。大概你可能在这边勉强，这边呢你还可以做 cascode。如果你的 supply voltage 是 2.5 伏以下呢，这是 very hard to implement。就是如果你上下，就是你想象一种状况，就是说。如果我家的房子呢是挑高的，那这个是挑高嘛？那我就可以上面做那个叫什么天花板，下面可以做木地板，把它垫起来嘛。那我可能 isolation 就比较好。 可是我家如果是那种那叫什么鸽子楼，就是那种夹层屋，我已经是夹层屋了，我就没有这个空间，我再做我就站不起来了，大家懂我意思啊？所以它基本概念是这样，就是说，所以为什么 Cascode 的结构呢，在 Advanced Technology node 就很难用，因为你已经夹层屋了，你已经 VDD 的电压非常小，所以你已经没有空间再去做这些 isolation， 就是做这些，就是叠加啦。因为叠加意思就是你做木地那个叫什么架高嘛，就是地板架高，然后天花板你都没有空间做这件事情，因为你会站不起来。OK， 所以这个是 technology 的这个演进的状况，会使得 Cascode structure 用的不太好用。可是呢，如果你今天是高压的系统，就譬如说你要做车用电子 ，for example 是高压的系统，你本身呢就有10几伏的话，那就可以做 Cascode。那所以 Cascode 的另外一个好处就是，如果你本身电压不是问题的话，那你可能可以就做 Cascode structure for gain 之外，它还可以做分压的工作，所以它是一个，我应该再写一个，它另外一个好处就是它是一个，另外一点就可以想象它就是可以。另外一端啦，就是如果你是要做高压的电路的话，那你可能就会希望做 Cascode 的结构，让电压分给很多人去降这个压，否则的话呢，你就会transistor会坏掉，所以你就可以用叠加的让这个电压分出去。所以它另外一个 purpose 呢，就是它可以做耐高压的结构。所以另外一点就是，如果你有耐高压的 circuit，那就可以用 Cascode structure， 同时可以得到它一些好处，然后做一下 isolation， 就是会比较怎么讲？会比较稳定啊，就是说它基本上是高压的电路，你大概是可以做这个。那低压的，如果今天就是说，如果你今天假设你今天的 design constraint， 譬如 for example， 如果我给你一个 platform 是0.18或是90，那你就不要再想了，因为基本上做这个结构会让你站不起来。这样 ，OK？ 好，那我想我们今天就讲到这边。那大家有什么问题可以？